Okay, hello everyone. It is 2 p.m. Eastern time. I've started the meeting and let you all in. Happy Wednesday. My name is Jade Kennan and I am the Knowledge and Impact Lead for the Young Professionals Committee of the Canadian Geotechnical Society. Today's webinar will be focused on the development of geotechnical knowledge through a case study of gravity retaining walls. This webinar will be followed by a Q&A period. Please, just a side note, make sure to type any questions you might have in the Q&A box and not the meeting chat, because I won't be checking the meeting chat. So our speaker for today, Dr. Laifa, is currently a senior principal geotechnical engineer at WSP and an adjunct professor at TMU and York University in the GTA. Laifa has a broad range of experience in building instrumentation and monitoring, geotechnical and hydrogeo investigations, shallow and deep foundations, deep excavation, tunneling, groundwater, roads, bridges and pavements, water mains, sewers, slope stability assessments and stabilization design measures, as well as in situ and laboratory tests. That is all to say that he has 39 years of consulting geotechnical and geoenvironmental engineering experience in both Ontario, and he obtained his PhD degree from Nanyang Technological University, and all his experience has been emphasized in the heavy civil engineering sector. He has also published more than 50 technical papers in journals and conferences, and is the author of hundreds of geotechnical engineering and research reports. He is also the lead author of the 4th chapter of the 2024 edition of the Canadian Foundation Engineering Manual. Somewhat more related to our webinar today, Dr. Cow has also served as the chair of Soil Mechanics and Foundation Division of the Canadian Geotechnical Society from 2021 to 2022. So needless to say, he's an incredible professional, and without further ado, the Canadian Geotechnical Society Young Professionals Committee is proud to present the 10th and the first of 2025 webinar in the Geotech 101 series. Take it away, Laifa. Thank you.
Thank you. CGS Young Community invited me to give my presentation. I try to share some of my experience during the engineering practice. Let me share my screen. Okay. Today's my topic, it is regarding how we gain the geotechnical knowledge through the case study or project experience. The outline of my presentation, firstly, I'm talking about what is the challenge in geotechnical engineering. Then talk about how we develop geotechnical knowledge. Then through this case study of the gravity retaining wall, finally give the recommendation. As we know, the geotechnical engineering, it is a very special career compared to the structural engineer or the civil engineer. The reason behind that, because the ground, we know the ground, it is variation, it is huge. Then we need to talk about the soil, rock, and the groundwater. For example, I just take one cross section for the recently project in downtown Toronto area. You can see that is for the railway station design. We have the fill material. It is for the abutment. Then below the abutment, the outside of the abutment of the railway, we draw the boreholes. Then the borehole spacing, it is only 30 meter to 50 meter. Then you can see what is the variation of the soil. In this case, The fill material, it is can be ranged from 0.5 meter to 4 meter. Then we have the local sandy soil. Then the thickness also varies from the 1 meter to 4 meter. Below, you can have the clay material. Even the clay material thickness also variation it is huge. Clay, for example, from the 3 meter to 7 meter. Also, the elevation of this clay material it is varies. Then below the clay material, it is the clay tier. The thickness of a clay tier, it is you can see the huge variation. Um, then we have the shear bedrock. For the shear bedrock, you have the with surface with the shear. Then below you have the relative fish bedrock. Sometimes we call it is sand bedrock. Then you also can see the thickness. It is a change or not. In addition, for this soil change, even the groundwater table variation also too much. We have two layer, at least two layers groundwater table, right? One it is from our bottom, another from bedrock. In the our bottom, then we have a piezometer. You find the variation of the water table can be 2 meter difference. Even in the bedrock, also the groundwater table is not the straight line. So give this change of the ground condition and then that is make not like the structure engineer. Then you have the concrete steel. Then that property relatively uniform. But for geotechnical engineer, we have this material, it is not uniform. Then how we determine the geotechnical parameter? That depend on the testing method, also depend on interpretation method. For example, in here, if you based on the SPTN value, use the traditional empirical equation. For example, people always use 6 times SPTN value for the Adjunct shear strength. You find that the Adjunct shear strength range from 0 to 72 kPa. Because SPTN value is 0, then go to the 12. You find this Adjunct shear strength from 0 to 72 based on the SPTN value. In this side, we also done some the fair wind ties. From the fair wind ties, we find the Adjunct shear strength relative in the is range from 64 to 90. From here, you can see the even for the same parameter, but your interpretation from a different testing method give you huge difference, especially from SPT. Give the some value, it is really the unreasonable. For example, the Adjunct shear strength is 0. Of course, that value it is unreasonable value. So for the geotechnical engineer, you need to make your own judgment which parameter or which testing method you need to use for your project. That is, you need most of the time you need to find out which method it is more reasonable method. Then which method can give you a big error. For the another things, it is regarding the equation or model. For the geotechnical equation or model, they also have the huge difference. For example, power foundation. You can use the alpha method, beta method, or you also can use the SPT and value, the cone penetration test, or parameter test. Even every year, they have a lot of publication in the journal paper, give you a different solution. But the key point is that all these methods, they have the assumption, limitation. We need to know what is the assumption or limitation in behind that model. That is the key point. How we How we build our geotechnical knowledge, of course, you have to attend the university lecture or attend the seminar, workshop, self-learning from the textbook, manual, and the code. Another, my opinion, another most important thing is very often can ignore. For the local government association, they also have its own regulations. For that way, you need when you do any project, you must know what is the local regulation requirement. That is very important. Sometimes because if you didn't follow the local regulation, then there could be come out additional claim lawsuit. For example, as I know, as one project in the Toronto area, then the Toronto, the local, the city of Toronto, they have a recognition for the pavement design. They have the thickness type of pavement design. If you didn't follow that regulation, you even the theoretically you use the material, it is working. However, if you didn't follow the regulation, then the contract can sue us a geotechnical engineer because our recommendation didn't follow the local regulation. That's why here I make it is a red corner. Make sure not only learning from the textbook manual code, you also must understanding what is where you're looking, which project you're working, what is the regulation code it is followed. Most important way, we need to gain our knowledge from the practice. You try to gain learning experience for your own project, learning from your mentor, or try to do some case study for each project. Another most important is lessons learning. We know most of the geotechnical knowledge developed, it is from lessons learning. Even today, we still find a lot of the failure. For example, here, that happened last year near the um, uh, Toronto near the railway, where after heavy rain, that is slope, it's a failure, right? Luckily, here we don't have any damage to the human because during that heavy nobody working in this site. Then that is even it is failure, but of course they have some damage for the utility, not for human beings. That is a good point. But from here, you can see for him here, that means they previously when they construction, the environment for the railway, they don't consider sufficient factor for this design, the slope. For example, for this case, main issue because of the drainage, not sufficient to discharge the surface water. Once the soil becomes fully saturated, the friction between the soil become loose, then come out this could be slope failure. Okay, today I try to review one project. What we in essence can be learning for this project. This project is where construction the roadway bridge of Saint Rear Line in Ontario. That is geotechnical investigation done in 2006. Then four borehole was drilled. Then following the geotechnical investigation, then we have the construction, the environment, and the retaining wall. The height of the retaining wall range from 2.8 meter over the existing environment, then to 7 meter on one side. Because this side, they don't have the enough space. So then they need a design for the retaining wall. Then from the geotechnical investigation, you can find what is the soil. For this side, we have the loose to compact sandy silt field. Over the loose sandy field, you have a very stiff to hard clay tier. Then you have most important here have one layer of soft form clay. Yeah, from this penetrometer, the undressed range only 20 to 40 kPa. Even though SPTN value it is from 6 to 24, it is formed to rise steep, but the actual undressed range it is quite low. Below, of course, in interior location, we always have this hard or very dense glacial tier. SPTN value it is greater than 50. For this retaining wall, the construction on the right steep to hard sealed clay tier. Then the also groundwater it is quite low. Based on this borehole information, then the geotechnical report it is prepared. They also give this design parameter for the retaining wall design. For example, they have a fixed angle. If you're looking this is a fixed angle, it is only 30 degree. It is not too high, correct? Then they also have the solar UV only give them 20. It is also not too high. Normally for the glacier tier, the UV could be more than 20. Then based on that, they also provide what is coefficient of earth pressure for design vertical load. They use 0.4. That value between the active spatial coefficient and the coefficient of spatial at risk, 0.4. That value is also not too high. I need to be conservative. However, they don't coincide. If this backfill is not horizontal, it is slope. Of course, that parameter could be too high. They also give the KP positive spatial for the field 2, then native soil 3 corresponding to 30 degree. They also give the sliding factor. Based on this borehole information, they recommend the soil bearing capacity is 200 kPa in SLS along the 25 millimeter settlement. Of course, in that geotechnical report, they didn't do the settlement analysis. They just assume then 300 kPa in US for this retaining wall finding on rise steep to hard silt clay tier. That value normally, if recommendation for the shallow strip or spray foundation, of course, it is reasonable. If you read the geotechnical report, most of the geotechnical report recommend this value for the shallow foundation design. However, does this value also applicable to retaining wall? No, of course, no. That's why this wall doesn't have this issue. Okay, based on that, the structural engineer designed the grabbing wall for this section at this site. You can see for the grabbing wall design, they use the high, it is 6 meter, then the wide it is 4 meter. The width divided, it is about more than 70% of the high. For most of the grabbing wall, that design also looks okay. However, they didn't consider you have 1 to 2 slope behind this wall. So then that's one become the wall, the same design, it is not so conservative as we originally assumed because you have the slope. If you have the slope, then the natural spatial cohesion will be small compared if it is the ground surface is horizontal, correct? Because in the geotechnical report, they don't consider that is a slope surface behind this wall. Okay, what happened? Shortly after construction, then they found the natural movement, vertical settlement. It is observation. Then the geotechnical instrumentation monitoring what is installed. They installed on the top of this retaining wall. You can see that during the during the monitoring from the within the 3 years, you can see from the vertical sediment, it is more than 140, correct, hairs. The natural movement are also more than 400 millimeter. Bigger natural movement already happened. That means the sliding already happened. Then that means the vertical sediment more than 140. That means the building capacity is not sufficient taking this grabbing wall. You can see here the pavement, it is the movement, this section, correct? Okay, then we have done the site investigation, observation in 2010, 3 years after construction. Take some photo, measurement the retaining wall. You can see from here. Then this wall damage already happened, correct? Local damage grabbing already happened. Then the soil become loose. Also the wall, for the highest wall, you can see this originally the wall design is inclined, not vertical. But after 3 years, this fence already push away. You can see this become the not vertical, even not vertical, correct? Originally design, they have the 1 to 7 inclination, but now this one almost vertical, even push naturally against this fence. You don't have any gap between this fence and the wall. Originally, they have some gap. Then you also the surface, the pavement have the crack. Then the drainage channel, it is become damaged. That means the sediment, it is not uniform, correct? Because you see here, they have the crack for the subdrain pipe, already cracked. That means the sediment, it is not uniform. Highest sediment happen in the middle of this retaining wall. Then after we measurement this wall, we find for the highest one, the some grabbing already push out. Then they also the design, it doesn't really follow the design drawing. The design drawing uses 1 to 2 slope, but actually it is 1 to 1.6 for the highest wall. So that means maybe during the construction, they no engineer monitoring the wall construction. Then you can see this for this wall, you basically it is already pushed away. The sliding resistance is not sufficient. Then they propose the backfill return slope. It is also higher than the design. That's why you have the sliding resistance is not sufficient. For this 5.5 meter wall, that is we found that generally it is following 1 to 2 slope, right? That is so. That means they, even though they need to be pushed, but basically it is not much damage. But for the highest wall, you can see some damage or failure, sliding failure already happened. For the gravity wall design, traditionally we use the working load design, but now we must follow the limited state design. For example, in the Canadian Foundation manual publication last year, they provided a different factor for different failure. For the base sliding, the typical value for sliding, it is resistance factor 0.8. They also give the range. If you have more investigation done, you have a good understanding of this project, you can use the higher resistance factor, can be reached 0.9. If you don't have the good geotechnical investigation, then you need to use lower factor, 0.7. The second one, it is considered overtending. That means the active moment against the resistant moment. You have a factor 0.5. They range from 0.48 to 0.55. For checking the obtaining, we also need to make sure the loading point ECC it is the next base of the wall divided by 6. The third factor it is regarding the building resistance. If you based on the limited slate design, you need to consider the low resistance, typically 0.5. The also can be range 0.45 to higher 0.55. Then for the limited slate design, in the new foundation menu, they also have the geotechnical resistance factor. They use 0.8 for the settlement and the diffraction. The range it is 0.7, low understanding to higher 0.9. The reason the new foundation menu following the Canadian Bridge Code, they introduce this new factor for the SRS loading. But in the building code, this factor still taking one. They haven't introduced this SRS resistance factor. Another new factor it is from the Canadian new foundation menu. It is consequence factor. That depends on what is the consequence of this building failure. Typically, it's 1. That means the damage to the people or property is normal. If you consider you have the higher damage, then you need to consider the lower 0.9 resistant consequence factor. But for the countryside, there will be no impact to the property or human beings. Then you can use a lower consequence factor 1.15. That is the new design method for retaining wall. But traditionally, people still use the working load design for the retaining wall. Regarding the sliding, it is 1.5, overtending 1.5 to 2, the building failure greater than 3. Another most important factor for the retaining wall design, it is global failure. They consider it is this wall can be global failure or not. That one still uses under the working load design. The factor safety for the global failure is 1.5. They haven't used in the limited slate design for this concept. The reason because most of the software used for the global failure, it is use the slope software, slope stability software. In that software, most of the software still use the factor of safety. That's why actually that concept is still based on the working load design. Then for the retaining wall, most important is the building capacity. For the building capacity, the retaining wall, since you have the natural earth pressure, then you have another factor, not only the building factor, also shape factor, inclination factor, tear factor, and the ground slope factor for the retaining wall in the construction retaining wall. Most important because you have the natural earth pressure, makes this building capacity for retaining wall, it is much smaller compared to the normal foundation. If you don't have any natural, that is, for example, you can use this formula, but this factor for each natural law, then different people could be give the different value. But the most important, you need to remember when calculation the building capacity of the retaining wall, you need to consider natural law impact. If you don't consider the natural law impact, of course, you will got the higher building capacity. Here, then we check what is the building capacity for this wall. Use the previous formula. Consider the what is the groundwater level in different elevation. For example, if we use the original report, then we find the average working load, it is 212 kPa. Then but the actual working load, they are different from the 120 to 180, correct? Then you use consider the different groundwater level. You also find the admit building capacity. It is different. They have based on the you assuming what is the groundwater level, what is the height, you can give them a different value. For example, original report they require US 300, then SLS they recommend 200. But the average working load already 212. It is greater than your SLS building capacity. Then the vertical stress in the at the foundation level, original report assuming 132, the 190 for the under the road. But the actual condition, it is a range from 80, 180 to 190. Then that means the building capacity, it is our estimate. Then the working load was what is underestimate, because the working load you have once you consider the natural spatial, of course, because you have the distribution on the wall, it is not uniform though. Then that's why the geotechnical report, original geotechnical report, didn't consider this working load in the design. Then we also can check what is sliding, overtending, and the global stability. For the all of the case, we find the overtending. If we use the working load design is 2, but basically for different water level and height, we find the 1.7 to 1.8 marginally is okay. However, if you use the limited slide, of course, limited slide 0.5 equivalent to 2. Of course, this wall, it is a little bit under design for the overtending. For the sliding, then if we use the 1.5 working load design, most of them for the highest wall, we find that it is cannot be reached 1.5. That's why you find that the sliding already happened, correct? Also, especially one case, it is only 1.15, close to 1. That's why the sliding could be happen. Then regarding the global stability, that wall design also less than 1.5, because all the cases the uh, uh, global against stability is less than 1.5. You can use some software easily come out what is the global stability. For this wall, we know this design, it is something is our design for the sliding, also our design for the global stability. Then most important things here for this project, since they have one layer of the soft clay, the soft clay could be have a long-term settlement issue. But for that project, since maybe due to that project, they originally geotechnical report, the geotechnical engineer don't have enough time to do this settlement analysis. But my opinion for the foundation or retaining wall, when it is a construction on the soft clay, especially they have a long-term consolidation issue. we need to do the settlement analysis. Yeah, since the sometimes we don't have enough budget for the conduct the geotechnical laboratory testing, for example, for the altimeter test, one-dimension consolidation test. Well, what you can do, then you need to try to got some of the parameter from the textbook or from the menu, foundation design menu. For example, if you taking the Bauer's foundation design menu, they have some typical consolidation parameter, C sub C, C sub R, say per consolidation compression index in NC stage, or the rate compression index on our consolidation stage. Also, they have some the secondary compression index. For the sandy soil, they also provide some the elastic modulus, the Poisson ratio. You still can find some the reference soil parameter from the textbook or design manual if you don't have the biology for the laboratory testing. Another way, you try to collect some parameter from the local project. For example, in the Ontario glacier tier, I tried the summary. What is the unit weight? What is the water content? Then also can be correlation to SPT and value. What is the fixed angle? Then also compare the perimeter types, SPT and value. What is the correlation between the perimeter modulus for the clay material or sandy material? You can see sometimes you still can find some the good relationship. For example, for the unit weight, they always reduce with the increased water content, correct? Because that is all reasonable. For example, the water content is higher, definitely you have a lower unit weight. Then also for the glacier tier, sometimes we find that the unit weight it is much higher than the traditional normal soil. You can see if water content in 15, then you find that the unit weight roughly about 21 to even to reach to 23.5. It is a high, correct, for glacier tier. Then the fixed angle also quite high. The minimum it is already 31, even SPT and value only 10. The highest one could be reached 40. That is the modulus also quite high for compared to the normal soil. Sometimes even the SPT and value is only 10, then the modulus can be reached 25. You see, of course that is not we cannot get a good relationship, but the trend it is there. That means when you have the higher SPT and value, the modulus, perimeter modulus generally is higher. Then you also try to collect some of the consolidation parameter for this local soil. You at least you have some reference. For example, for the glacier tier, we have the relative the no compaction index. They also the right compaction index need to be no. The void ratio it is from 0.25 to 0.46. This parameter generally it is lower than the traditional clay if you find from the publication. Then you also for the of course it is not glacier tier. That is compression index need to be higher compared to the glacier tier. Correct? Another parameter you also try to find out what is our consolidation ratio. Maybe it can be related to the SPTN value or Fairwind test or the laboratory test, because that is three important parameter if you use to the settlement analysis for Canadian soil. Okay, for this project, then we can do some of the settlement analysis. The currently we have another one software. For example, you can use the slide SATO 3D, or even finite element analysis. Once you use the based on the soil parameter, based on your local experience, when you add to the software, then you easily can come out what is the settlement for this project. For example, I try to compare what is the production value and what is the measurement. That is, I found that this value is quite consistent, correct? The measurement it is from 100 to 20 to 140. Then the production it is roughly about 125. You see the trend it is quite close. That means even you don't have the batch to do the laboratory tests, but if you try to compare what is the local soil parameter, you still can get the good result. And at least you have some range of this settlement. For example, if I believe if for this in the beginning of this project, if the geotechnical engineer realize and this loading, this clay soil will be settled 100 more than 100 millimeter, of course, they will be changing the design, correct? Or make this wall even more wide, or make some of the reinforcement behind this retaining wall. Make the vertical load distribution, it is in big area, or do some soil improvement, or another way, it is payloading, correct? If the time it is long. Then how we um, um, modify, improve this work? Of course, you can give the different option. For example, we can use the soil layer. Then also we reconstruction the wall use geogrid. Or another way, we try to reduce the vertical load, right? Use the net weight material. Finally, you also can do nothing, but the keep maintenance. For this case, where they decision make the do nothing, continue monitoring. Then you can see from here, after a few years, the wall, near this wall, we still confronted the crack because the original design, the factor safety is too low. That's why this wall will be continue deform, right? But the most important thing is things here, they don't have the building. They only have some farmer. That's why they just keep continue monitoring because that it could be more economic. And the client need to realize that that wall could be still settled for another 100 millimeter until the clay it is fully saturate, fully consolidate, and the loading of this environment. Also, they need to keep the resurface of this pavement, correct, for this road. Okay, what is license from here? I think a big license is that for the retaining wall, you need to always consider the working pressure on the retaining wall. It is higher than the vertical because you have a natural spatial contribution. Then normally, if you don't have during you do the geotechnical investigation, if you don't have time um, to the detail analysis for the sample assumption, you can assume the working pressure could be 150 to 200 of vertical load. For example, if the vertical load can, for the 4-meter retaining wall, it is 80 kPa, but on the top of this wall will be reach 100 to 160. That is increased because of the natural earth pressure. Then second point for the building capacity for retaining wall design, most important, you need to consider the natural earth pressure. rather than just without consideration the natural earth pressure. That means for the building capacity, if the without the natural earth pressure, maybe you assuming it is 200. However, if you consider the natural earth pressure, maybe only 100 kPa, you need to make some deduction. Then another most important thing, if the soil you have underlined by some stuff to form clay, because the clay could be have a long-term consolidation issue, then you need to use you need to estimate what is the settlement, because the settlement could be make this natural defection, also the damage the drainage pipe, then that make this wall base even worse. For this case, since they have the settlement, also the settlement not uniform, then we find that during the raining time, the base of the retaining wall it is fully saturated. When the water it is saturated the soil, of course the soil capacity will be reduced. Another thing is for the when you do the prepare geotechnical report, we need always to comment to the global stability analysis. Then also the sediment analysis must be done if they have the weak or loose soft clay material. But for geotechnical engineer, since sometimes when we prepare the geotechnical report, the retaining wall design it is haven't complete. What we should do to do, then we need to mention in our geotechnical report, tell the design engineer, the drawing must be reviewed by geotechnical engineer. Make sure the geotechnical engineer recommendation will be added in the design drawing. Another thing it is review the construction construction drawing. Make sure the construction have the good quality control, correct? That is not so. I have prepared some of the paper for this case study in the Canadian annual conference. If you are interested, you can go to the Canadian and Geotechnical Canadian Society website. From there you can find some paper. Not only for me, also I believe every year another one the geotechnical engineer prepare publication, another one case study for young engineer. Better go there, try the landing from the previous loose some good case study or gain some more experience. Okay, finally, thank you. Any questions?
Hello. Thank you so much, Laifa. I love the amount of detail you went into, and at least for me as a young professional, I always appreciate when people like yourself share the data alongside the images of what's out there in the field. It really helps to take all that knowledge and visualize it to the best of our ability. Right now, everybody who's listening, if you have any questions, please feel free to type them in. I'm actually now monitoring the meeting chat and the Q&A. So if anybody has any questions, please do type those in. Thank you. And Laifa, I love that you mentioned that everybody can access the past conference papers and sort of proceedings on the CGS website. That's a really good point to make. I am
Yes, yeah. I find
those
this,
out today.
CGS the website they have another one good material. It is for young professional. Better sometime go there to have a search. If you have some project, if you have confidence, you try the learning from the case study or from your mentor in your company. Yeah. Also, now I find that we have even from the website, sometimes you easily find your information. Now we know that now the AI, it is much become more popular. For the self-learning will become much more easy. For example, last week when I tried to find some the local building code, local recognition for the pavement design, the thickness, um, I, I cannot find it. Then I go to the AI. Then once I type the question, then they mix up AI immediately give me answer. Say where you can find that information, what is the requirement. Yeah, I think now is learning or getting information. It is much more easy.
Yeah, AI is pretty impressive. I need to certainly use it more.
Yeah,
Okay.
even for some the preliminary design, I believe some AI also can give you preliminary answer. For example, as I know for the power foundation design, some software already it is if you import the soil parameter, they can give you the recommendation. What is the power length? What is the capacity? But of course, you need to double check by yourself based on the local soil parameter. Yeah, but it's a good reference.
Yeah. No, that's a good point. Double checking AI's work.
Yes, correct. Yeah.
It doesn't seem like we have any questions from our audience. Oh, hang on, one just popped up. An individual presentation, and thank you for joining. Their question, Laifa, is what are the impacts of soil variability in the results of the stability analyses?
Yeah, I think what you can do, you try to select the lower band and up band. Also, make sure you take the range of the parameter. It is more reasonable. Actually, in the software, you can do the reliability analysis. If you provide, for example, fixed angle 30 degree plus -2, the software can give you what is the range of the factor of safety. Try to do some of the variation reliability analysis for the slope analysis. Also, for the slope analysis, you better use the residual fixed angle rather than you use a peak fixed angle.
Thank you. I hope that answers the person's question. A sort of non-technical related question. Yes, thank you, Chelsea. Yeah, for anybody who's wondering, and Dr. Carr as well, if you'd like to watch this back for whatever reason, we will be posting a recording of this onto the CGS Young Professionals Committee YouTube
Yes, of
page.
course. I can forward my presentation to you. Yeah.
Awesome, thank you. So I think the link to the YouTube page has been posted in the meeting chat. Also, once it has been posted, I will be sharing on LinkedIn the fact that it's up and available. I think we'll leave it at that, Dr. Kao. Thank you so much for your excellent talk. Me and the rest of the CGSYP committee are very honored to have you speak. For the audience, just a note, the next webinar on the Geotech 101 series will be on April 16th. So please follow the CGS LinkedIn page to make sure you don't miss that pre-registration link. And another thanks to both Dr. Kao and you, our audience, for supporting the Young Professionals Committee in fostering the next generation of geotechnical professionals. Okay, thank you.
Okay, thank you. Thank you, everybody.
Bye-bye.
Bye-bye.